Hi, my name is Xian and this is lab 4. Moving on to the objectives, we are observing the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We will utilize fundamental principles including both the momentum principle and the energy principle and other concepts such as Hooke's law, and we will see that the spring mass system does satisfy the energy principle. So here, as you can see on tracker, I set my axis here to the fixed attachment point, and I set my calibration stick to 7 from the fixed attachment point to the mass. And if I play this video for you, you can see that the mass is oscillating in this like circular motion, and it's being recorded here in these two graphs. So moving on to some why this is. So the formula that I used was T is equal to 2 pi square root of m over k, where T is the period of one oscillation and m is the mass, where nk is the spring constant. So from tracker, we found T to be approximately 1.52 seconds for one complete oscillation. If we substitute T into the equation, we find that K is approximately 6.88 newtons per meter. If we just kind of manipulate the formula a bit, we can find that. And to find the relaxed length, we know that at static equilibrium, where the mass is just hanging from the string without moving, the gravitational force and the spring force are equal. So I set Fg equal to Fs, where Fg is mg, and Fs is Ks, where S is just L minus L naught. So if we kind of manipulate the formula a bit, we find that L naught is equal to 0.13 meters. So as you can see from my code over here, I set the mass of the ball to 0.402. I set the position equal to negative 0.111 and negative 0.63, and I set the ball velocity, initial velocity, to 0 because it's not moving. Over here, this is just reading the data from the CSV file that has the position data from tracker. Over here is my time step. And over here in this section, I just input the constants that I just found. G, we already know to be 9.8. Ks, we calculated. L naught, we calculated. And over here, we find that L is just the position of the ball minus the spring position. L hat gives us our direction. And S, if it's greater than 0, that means the system is being stretched. And if it's less than 0, then it's being compressed. So over here, if I show you in my PowerPoint, these are the formulas. We know that kinetic energy is 1/2 mv squared. Potential gravitational energy is mgy. Potential spring energy is 1/2 ks squared. And those are the formulas right there. So moving on into our code right here. This entire section under the while loop is just kind of constantly updating the position of the ball. We know that gravitational force is just mass times g, negative mass times g. The spring force is negative k times s times L hat, and then F net is just the summation of the spring force and the gravitational force. And over here, these two formulas are just from Newton's second law to predict the new position and the new velocity. So as you can see right here, this is what we had before, and we're just kind of constantly updating the spring, like I said. And here is the calculating the energy changes. We know that K, which is our kinetic energy, is 1/2 mv squared. This is delta K is just a change where we have the final kinetic energy minus initial kinetic energy. Ug is just the gravitational potential energy. Just delta Ug is calculating the change. Us is the gravitational, spring potential energy, and then delta US is just calculating the change in the final minus initial, and then we just plotted all those with T and also the summation. So if I run it for you right here, the blue arrow is the spring force, the black arrow is the gravitational force, and the blue ball is just the mass. And as you can see on the right, it's just plotting all of that, and I'll get into detail on that a bit later. So after comparing the graphs, this top graph is from tracker, which analyzed the position, and then bottom graph is the one we just saw from V-idle. And so they're not exactly matched, probably because of human error. I probably didn't pick the right center of mass in tracker. And as you can see in the bottom graph, that illustrates the energy changes. The blue line is delta K, the red line is delta Ug, US, sorry. The green line is delta UG, and the yellow line right here, it's kind of hard to see, is the summation of the forces, and it's 0 because energy is conserved. Our delta E is 0. What this means is that in our system, we included the mass, the spring, and the earth, which makes it 0 right here. So what does it mean? Is the energy principle satisfied? And the answer to that is yes, because we, as I stated previously, delta E is 0 because we included everything in our system. As you can see from this yellow line right here, the yellow line represents the sum of the energies. So moving on to the second question, what changes if I calculate the period of oscillation using the X position data versus using the Y position data? And they're different because for X, I found 1.52 seconds, and for Y, I found 1.37 seconds. This is because for X, it goes in a horizontal pendulum motion, so I use this formula, while the Y data, it goes in an up and down spring motion, so I use this data. So they're supposed to be calculated differently. Thank you so much for watching.